think there's a time that happens to the life of every good photographer when you suddenly know you've gotten serious about photography. It's that moment that you realize you're no longer content to just take pictures. That's not good enough. Now you want to make pictures. Well, when you find yourself getting up in the middle of the night to be in a place like this, to be ready for a sunrise, then you know. Because there might be magic in this sunrise. There's that possibility that this sunrise will have that one instant of time, that moment of visual poetry, that music that's never been played before and may never be heard the same way again. So you're here, just in case the magic is here, and you're ready. Because you know if you want to capture the magic on film, you have to understand it. You have to know where magic is likely to appear and when. You have to know how it's likely to behave. And most of all, you have to know how to control it. I'm Brian Ratty, and the magic is light. So what is this magical thing we call light? If you ask a scientist, he'll talk in precise terms. He'll define light as that portion of electromagnetic spectrum that normally stimulates sight. But if you ask a visual artist, he'll probably talk about light in a little more emotional terms. Terms like hard, soft, warm, cool, even romantic. But how should we as photographers look at light? To me, it's energy. Light is the energy that puts the image on the film, the essence of all photography. It's significant that the word photography, which comes from the Greeks, literally means to write with light. Of course, if light is the essence of what we photograph, it's also the essence or medium of what we see, our sole visual link to the world. Okay, so how do we approach light? How do we learn to understand it, control it, use it to make better pictures? In this program, we'll look at the 4 properties or conditions of natural light that concern us the most. They are direction, form, what I call hardness or softness, contrast, and color. We'll see how these 4 characteristics of light influence what we see and photograph. And we'll look at some ways we can creatively control them in our photography.
Key concept. Light is the essence of what we photograph. Key concept. The word photography comes from the Greeks and means to write with light.
There's only one principal source of natural light in our world, the sun. We're comfortable with the sun. It doesn't matter whether we're indoors or out, or if it's night or day. Psychologically, human beings expect to see all objects lit as the sun would light them, with a single source from above or from one side, and with a single shadow. The direction of the light source is revealed to us not only by the shadow it casts, but by the reflection of the light as well. Because light travels in straight lines, it always reflects off the surface at the same angle at which it strikes it. In other words, the angle of incidence equals the angle of reflectance. It's a law of physics, and it's important because it allows us to predict the directional effects of light. For instance, we know that light rays striking a surface from the right will be reflected to the left. Light coming from above and behind the subject will be reflected up and to the front, sometimes directly into the lens of our camera. It's not always easy to see the angle of incident law at work. Take the grass in this meadow, for instance. It is made up of an infinite number of tiny surfaces, each presenting a different angle to a single angle of sunlight striking it. And what's happening is the rays of light reflecting off the meadow are no longer organized into one straight line, but are scattered to many different angles of reflectance as there are angles of incidence. That's why we can't see the concentrated reflection of the sun in the grass. But sunlight can be almost blinding when reflected off a flat, smooth surface like a pool of still water or the wing of an airplane, because there's a single angle of reflectance. The beam of reflected light reaches our eye or our camera concentrated and nearly intact. Of course, we can control the amount and quality of the light reflecting directly from the subject to the camera by changing the relative position of the camera, light source, and/or subject. So far, we have seen how more or less solid objects reflect light directly from a single source, the sun. But this side of my face is not being lit directly by the sun, yet there is light there. It's called ambient light, and you find it to a greater or lesser degree anywhere you find direct light. Ambient light is light which does not come from the primary light source. In fact, it has no directional quality at all. It's random light, reflected by the total environment around us. The ground, the sky, the walls of a room, even dust particles in the air. Ambient light provides a lighting environment the way air tends to occupy a vacuum. It creates no obvious light or shade effects, and it keeps shadows from becoming totally black. Let's see how we can manipulate the directional quality of light to convey different moods, different kinds of information about a subject. When directional light strikes an object, it defines the object's shape. How? By delineating three areas. A highlight appears as a very bright small area on the subject because it reflects light directly into the eye or the camera. Usually, the reflected light is so bright you can't see surface details in this area, and neither can your film. The lit area is bright and illuminated directly by the source, and you can see surface details. The shadow area is shaded from the light source by another part of the subject. There is little or no detail. The combination of these three areas gives the viewer information about the shape, dimensions, and texture and color of the subject. The shadow and lit areas, and the boundary between them, show us the object's shape. The lit area shows us the subject's color. Texture appears at the edge of the lit area where light strikes surface irregularities from the side. When we change the directional quality of the light, either by moving the light source, changing the camera position, or reorienting the subject to the light source, things begin to happen. The angles we choose depend on where we want the highlight, lit, and shadow areas to be, and what type of information we're trying to convey. And of course, a great deal depends on the type of subject, the overall mood or feeling we're trying to achieve. The possibilities are limitless. Okay, so what have we seen about the directional quality of light? First, that human beings expect to see objects lit from above or from one side with a single shadow the way that the sun lights them. We've seen that the angle of light reflecting off an object is equal to the angle of light striking that object, but that different types of surfaces reflect more or less light in more or less organized ways. We know that ambient light is directionless light. We have seen how the highlight, lit, and shadow areas created by light reflecting off the subject show us the subject's shape, form, color, and texture, and how by actively changing the relationship of the light source to the subject we can creatively control the mood or the feeling we want in our photograph. And that's the important thing. We as the photographer must not only understand the directional quality of light, but we must be able to creatively control that quality.
Key concept. The only principal light source in the world is the sun. Key concept. The angle of incidence equals the angle of reflection. Key concept. Directional light defines the objects we photograph.
We have seen how the directional quality of light plays a critical role in illuminating and defining your subject. Now let's turn our attention to something equally as important: the nature of the light source and how its relative size and distance to the subject will help determine how your subject will appear in the final photograph. The sun is a very large light source, but in relation to its distance from any object on Earth, it's quite small. It's so far away that the light rays it produces are essentially parallel. When shining directly on a subject on a clear day, it always produces hard light and casts sharply defined shadows. But when the sky becomes overcast by a thin layer of clouds, the sun is no longer the direct source of incident light. Instead, the sky itself becomes the direct source. Because it is very large in relationship to its distance from any subject, it provides a soft light with indistinct shadows. So which is better, hard light or soft? Let's look a little closer at the effects of each. Hard direct light has an uncompromising quality which makes it unsuitable for subtle effects. Its starkness emphasizes bold shapes and colors. It produces black, sharp-edged shadows which become important visual elements in the scene, as important as the objects themselves. It creates brilliant, compact highlights with strong modeling of form. Hard light weakens pale colors, but makes strong colors more brilliant. Softer, more diffuse light creates weak, soft-edged shadows. It reveals fine detail and a wide range of subtle tones, colors, and shapes. Soft light gives muted colors delicacy and depth, and makes strong colors richer. The real advantage of soft light is that it helps to keep the composition simple. It unifies form and detail because shadows and highlights don't complicate the picture. Between the very hard and the very soft light source, there is the medium, and it is usually the best choice for photography. Medium source lighting gives excellent modeling for shape and roundness. The highlight is not so large and bright that it obscures the lit area. The directional quality of the light is still strong, and shadows are not as sharp and distracting as they would appear in hard lighting. You can find a medium light source indoors or out. This window is a good example. Or sunlight bouncing off a lightly colored wall. Sometimes in stormy weather, the clouds will part to reveal a brilliantly lit cloud, a dramatic example of medium source lighting. In fact, changing weather is the magical time for photography. Some of the finest pictures ever made were shot in some of the most uncomfortable weather, in rain, snow, storm, or fog. Because when the weather changes, the light changes. Unexpected things can happen then. Beautiful things.
Key concept. Light form has three basic properties: hard, soft, and medium.
We have seen that when directional light falls on an object, it helps define the area of highlight, light, and shadow. In other words, it creates a relationship between light and dark. And it is this relationship that forms the contrast quality of light. We can do powerful things with contrast in photography. By increasing contrast, we can sometimes add impact to a picture. We can convey feelings of simple strength and power. By decreasing contrast, we can convey the opposite emotions, like delicacy, beauty, and calm. But in order to control contrast, we first have to understand the difference between how we're able to see it and how the film is able to record it. In short, we have to learn how to measure it. But first, let's look at contrast in two different ways. The first I'll call lighting contrast. It's the contrast created strictly by the light falling on the scene. It does not depend on the subject or the elements within the scene. When we look at lighting contrast, we look at the entire range of brightness within the scene, from the brightest highlight to the deepest shadow. The second way to approach contrast is what I call local or subject contrast. Local contrast does not depend on the directional quality of light. It's created by different tonal qualities inherent within the subject itself. For instance, you see the jacket that I'm wearing as a very black tone, while my shirt is a much lighter tone. The light striking both my jacket and my shirt are exactly the same, yet the inherent light reflecting qualities of my jacket and shirt are different, creating two adjacent local contrasting tones within this one scene. What's important is that the total tonal range of what we photograph is made up of both kinds of contrast, the light and shade effects of light itself and the tonal differences inherent within the subject. So how do we measure contrast, and why should we bother? Well, we wouldn't have to bother if our film could record the same brightness in a scene as our eye sees it. But in general, film has a much narrower range of brightness. What appears to be acceptable to our eye in contrast is often too great for the film. So if we can't trust our eye, how do we make precise measurements of the brightness differences from light to shadow? Here's one good way: the incident light meter. It measures only the light falling on the scene. From the subject's position, you first measure the light falling directly on the portion of the subject lit by the main light source. F11 and 1/25. Then you measure the ambient light falling on the subject's shaded side. F45. That's an exposure difference of 3 stops. The typical light contrast for a subject lit by the bright sun on a clear day. We call this brightness difference the light ratio, and in this case the ratio is 8:1. The lit side of my face is receiving 8 times more light than the shade side. Each time the light to shade exposure difference increases by 1 stop, the light ratio doubles. A 1-stop difference is a 2:1 ratio. A 2-stop difference is a 4:1 ratio. And a 3-stop difference is an 8:1 ratio, and so on. If there's no measurable difference between the light and the shadow readings, the light ratio is a 1:1. There are no highlights or shadows. In a 2:1 light ratio, or a 1-stop difference between the light and the shade, contrast is very low, but just strong enough to reveal the directional influence of the light, and the light and shade effects it creates. The film easily records detail in both lit and shaded areas. A 4:1 or a 2-stop difference is the average light ratio for most kinds of photography. It has good visual impact. Light and shade effects are firmly established by the directional influence of the light. An acceptable amount of detail is recorded in both lit and shadow areas. But for some scenes that have an inherent wide range of subject tones, a 4:1 ratio may be too high for the film to record all the information in all the areas. 8:1, the 3-stop difference typical in ordinary outdoor sunshine, doesn't seem like a very high light ratio to the untrained human eye, but it is in photography. Ratios of 8:1 or even higher can be used for great dramatic impact. But with most subjects, some areas of the scene will fall outside the reproduction limits of the film. Shadows lose detail and appear as black abstract shapes. The point of this is that our choice of light ratios will have a profound effect on the look and feel of our photographs, and on the types and amounts of information they convey. So a serious photographer has to know his light ratios, and we're not always going to have the chance to do comparative light readings each time we set up for a shot. That's why you have to train your eye to see contrast the way the film sees it. And remember, you're the one in control. The way you use the contrast quality of light depends on how you interpret your subject and on what you want the viewer of your photograph to feel.
Key concept. There are 2 types of contrast in photography: light and subject. Key concept. It is best to use an incident light meter to measure light ratios. Key concept. Both film and the digital media have a limited brightness range.
You know, you could study color for a lifetime and still run out of time. Color is complex, fascinating. It spans such great divisions of human knowledge and experience. Physics, physiology, psychology, even human emotions. Color is sensuous, powerful. It conveys information about our surrounding. It creates strong moods and feelings. Color defies easy definitions. For each of us, relate to color in our own unique and personal way. To many photographers, the control of color is just the process of casual selection. We point our cameras at the colors we like and usually get beautiful results. But if we are to learn how to deliberately manipulate and control color, we must know and understand three things: the color of the light, the color of the subject, and the color potential of our film. Light, visible light, is energy radiated by that small portion of the electromagnetic spectrum. When these wavelengths of visible light energy are separated out by absorption and reflection in the world around us, we see them as color. Long wavelengths as red, shorter ones as blue, and all the hues in between. The color we see around us is caused by reflected light. Objects appear colored mainly because their surface pigments absorb some wavelengths but reflect the other. This red boat, for instance, is reflecting the red wavelengths but absorbing the rest. We can see the spectrum of colored light in a rainbow, or by passing a beam of light through a prism, as Isaac Newton did. But for most of the time, these varying colored wavelengths combine and register in the brain as white light. For instance, we think of daylight as white light, but is it? The fact is, daylight changes color constantly, from sunrise to sunset. At midday, when the sun is overhead, its rays pierce the narrow band of atmosphere at a perpendicular angle. Molecules of air scatter more of the short blue waves, but less of the longer green or red ones. The short waves are bounced around, making the sky appear blue, while the longer green and red ones pass through and combine, making the sun appear bright yellow. As sunset approaches, the light travels through much more atmosphere. Far more short waves are scattered. Only the longest get through. The sun appears red, and the reflection of this light from the clouds makes the sky pink. We only notice the color of daylight at times of extreme changes, like dawn and sunset. The rest of the time we view daylight and artificial light as white or neutral. Our brain makes this adjustment to keep us comfortable. If it didn't, food in a supermarket lit by fluorescent light would take on a greenish yellow look. A friend's face would look reddish orange in candlelight. In other words, we see the color of light as it really is, and that's the way our film sees it. There is no pure white source. Each source of light has its own ratio or balance of long and short wavelengths. This color balance depends on the color temperature, and we measure it in degrees on the Kelvin color temperature scale. The lower the color temperature, the redder or warmer the light. The higher the color temperature, the bluer or cooler the light. Artificial light sources, like candlelight and ordinary household bulbs, have a high red content and fall at the low end of the scale. Tungsten lamps, at 3200 degrees, are higher up, but still in the warm range. Overcast daylight at noon is rated at 6000 degrees, way up in the blue end. Two of these color temperatures are particularly important because almost all color film is balanced to one or the other. 5400 degrees Kelvin, the standard for daylight type color film, and 3200 degrees Kelvin, the standard for tungsten film. The point is simple. When the film is used in the color temperature of light for which it was designed, you can expect the results to have a neutral color balance. In other words, the light in the finished photograph will appear white, just as it originally appeared to your eye. So matching the color balance of the film to the color temperature of the light is the first step in controlling color for neutrality. And for much of what we do, it's enough. A strobe light, when used with daylight film, will consistently produce a neutral color balance, as will quartz light when used with tungsten film. But what if the film you're using is not balanced to your light source? Let's say you want to take an indoor shot using incandescent light, but your camera has been loaded with daylight film. You can use one of these. They're called color conversion filters, and they're handy to have. They convert color film to the illumination of a different type. An 80A filter converts daylight balanced film to 3200 degrees Kelvin. An 85B converts 3200 degree Kelvin balanced film to daylight. But the primary tools for controlling color for neutrality are these. They're called color compensating filters, or CC filters. They come in these gelatin squares which drop into a filter holder like this. The CC filters come in 6 primary photographic colors and in varying strengths or densities. What they do is absorb excess or unwanted color. Cyan absorbs red, magenta absorbs green, yellow absorbs blue, and so on. Here's an example. The cool white fluorescent lights in a modern office put out an unequal amount of green wavelengths. Color films, which are not balanced to fluorescent light, will record this unpleasant greenish cast. But a CC30 magenta filter used with daylight type film absorbs the green, producing a neutral result. We can use CC filters or combinations of them to warm up a scene we feel is too blue, or cool down a scene that is too red. There are no formulas, no hard and fast rules. In fact, sometimes we might want to filter not for neutrality, but for the opposite effect. The only real rule is experimentation. Try using CC filters for both neutrality and color enhancement. Then by evaluating your results, you can decide which one works for you.
If you're using a digital camera, this media color balancing is called white balancing. On the main menu of your camera, you set this balance by telling your camera's electronics if you're shooting outdoors, 6000 degrees Kelvin, or indoors, 3200 degrees Kelvin. Many camera systems also offer a third option, manual white balance. If the images are important, this is my preferred way of white balancing. On some cameras, this manual white balance is found on the outside of the camera itself. White balancing a digital camera is just like film selection for a film camera. Very important.
So far, we've seen how light forms color, and how the color we see is different from the color our film records. Now let's look at some specific colors and how they relate to each other. The visible spectrum contains 7 wavelengths or hues, but these can all be produced by mixing the light of 3 colors, red, green, and blue, the primary colors of light. Added 2 at a time, these primaries produce 3 new hues, the complementary colors, magenta, cyan, and yellow. Cyan, for example, contains green and blue, and is complementary to or forms white light with red. Color itself can be the subject of your photograph. More often, it's an essential part of your picture structure. It defines shapes, patterns, and textures. It conveys distance. It determines mood and invokes an emotional response. By learning to recognize the particular effects and the ways that colors relate to each other, you can begin to design with color and use this powerful language in your pictures.
Key concept. To manipulate color, you must know the color of the light, the color of your subject, and the color potential of your media. Key concept. Light color is measured in Kelvin temperatures. Key concept. Light's primary colors are red, green, and blue.
The most obvious controls over the exposure are the camera's aperture and shutter speeds. Working in conjunction with the film speed, these mechanical adjustments regulate the amount of light reaching the film. I'm sure most of you are very familiar with f-stops and shutter speeds, so bear with me for a moment while I do a quick review. The aperture is designated by f-stops and represents the size of the aperture's opening. The shutter speed is simply the amount of time the shutter is allowed to remain open. These two settings are interdependent. Each increment of either setting results in a doubling or halving of the light reaching the film. For example, if you change the f-stop setting from f8 to f5.6, you are doubling the exposure. Likewise, if you want to cut the exposure in half, you could either change the f-stop back to f8, or you could increase the shutter speed from 1/60th to a 1/25th. Either way, you would be cutting the amount of light reaching the film in half. The choice is yours, and it's usually determined by the creative effect that is desired. You might choose a relatively small aperture for the resulting large depth of field, or you may want to separate your subject from its background with a narrow depth of field by selecting a large aperture setting. In either case, the shutter speed will be dependent upon the selected aperture. On the other hand, you might choose a fast shutter speed to freeze the action, or a slow shutter speed to blur it. In either case, the same exposure is achieved by adjusting the aperture proportionately. These concepts are very important. If you have any doubts or questions, I strongly recommend that you refer back to your camera's manual or a photography text. A thorough understanding of the relationship between the aperture and shutter speed is essential for the creative control of exposure.
Key concept. Shutter speeds control the amount of time. Key concept. The aperture controls the volume of light.
The light meter is a tool that allows the photographer to accurately measure light. It can't think, it can't make decisions. That's up to you. As a photographer, you must balance the meter's data along with your own knowledge, past experience, and intentions for the photograph you're about to make. But before we talk about the meters themselves, let's take a close look at the measuring process. In photography, the most common unit of light measurement is the foot candle. Simply stated, a foot candle is the amount of undirected light measured from a standard candle at a distance of 1 foot. If there are 2 candles, then the measured light would be 2-foot candles. Now, as the light gets further from the candle, it is covering a larger area and is consequently less bright. There is a mathematical equation called the inverse square law, which defines this effect. If the light is undirected, as with a candle, then the light is falling off to the square of the distance traveled. When the light is directed, such as focused through a lens or bounced from a studio's lamp's reflector, then its diminishing brightness might not precisely match the inverse square law formula, but the general principle still holds true. That's why a flash is of little or no use in a large theater or stadium. Remember the inverse square law, because you'll encounter its effects throughout your photographic career. There are many styles of light meters available. The one I'm sure most of you are familiar with is the built-in meter found on virtually every modern 35mm camera. It also has an automatic mode. But just remember, it might be automatic, but that doesn't mean it'll be automatically right. I strongly recommend that you only use your camera's automatic mode in instances where the speed of the subject's action makes it difficult to meter the scene manually. Otherwise, keep the camera's meter to the manual position. You'll learn a lot more, and as you learn, your photographs will improve. The built-in meter can be very useful. Its main advantage being that it measures light passing through the lens. Any idiosyncrasies of your camera and lens are automatically taken into account, since the light hitting the meter's cell is identical to the light which will hit the film and make the picture. There are 3 common types of through-the-lens or TTL meters. An averaging system uses twin cells whose output is then combined to average the amount of light hitting the film. A popular variation of this is the center-weighted meter. In this system, the twin cells are overlapped in the center so that more emphasis is given to the center of the picture. The third style is the spot meter. Due to the very narrow area metering the subject, the photographer must be extremely careful. We'll talk more about spot meters in a few minutes. But first, let's look at the principles of the reflected meter. This is a handheld incident and reflected light meter. By sliding the bulb at the top away, we'll use it as a reflected meter. Like the reflected meters built into our cameras, it measures the light reflecting off the subject. Its main advantage is that it is more sensitive and accurate than the built-in meters. No matter what style of reflected meter you're using, just remember that it will only meter at what it's pointed at. And another thing, it can't distinguish between dark objects, medium gray objects, or highlights. Well, how do we decide then where to meter? Well, if this were an average scene, we'd point it at the entire scene and take an average reading of the subject to be photographed. Unfortunately, not all the subjects we photograph are average. Since the meter has no mind of its own and is totally colorblind, it would assume that this scene is of average brightness and would dictate an exposure accordingly. Likewise, it would indicate an exposure that would render this snow as an average scene. In each case, the meter wants to render the scene in medium or gray tones. That's because reflected meters are calibrated to a gray of 18% reflectance. This test card can be purchased at most photo dealers and is the standard upon which reflected exposure readings are made. When you point your meter, whether it is a handheld or built in through the lens, it will assume that it is being pointed at an average gray and will indicate a reading to produce that gray. In other words, if you want to photograph to resemble the scene as your eye sees it, you must meter on this value of gray. By doing that, all other tones, light and dark, will be rendered to their appropriate value. One method of reflected metering actually uses the test card. By placing the card in front of the subject and halfway between the light and the camera, a reading can be taken that will yield a photograph of good overall tonal quality. The test card acts as a reference area of known reflectance. It's useful for calibrating a meter or comparing one meter to another. It is also quite useful for work requiring critical exposure control. The card itself can be placed in the picture as a guide during printing. That way, there is a known reference tone for the printer to match. It is also quite useful for metering copy work. If the meter reading is based on the test card, then the overall tonal values will match the work being copied. In this case, I'm metering this part of the scene, since its tonal value is about the same as that of the test card's gray. By the way, a Caucasian face, or the back of a hand, comes close to middle gray. That's why the subject's face is commonly metered. In landscape photography, a green lawn is often used because its tonal value is close to the test cards. Just remember, whether you're shooting black and white or color film, your meter is designed to produce an exposure with a tonal value of approximately 18% gray. Another type of reflective meter is the spot meter. It's identical to the other types of reflected meters, except that it is extremely selective. While a normal reflected meter may read an angle of about 40 degrees, a spot meter will cover a far smaller area, anywhere from 10 degrees down to 3 degrees, or even as little as 1 degree. Although a spot meter can be quite useful, especially in the zone system, which we'll cover a little later, the majority of the time you can get the same results by moving in a little closer to your subject with either your built-in or handheld reflective meter. The most obvious distinguishing characteristic of an incident meter is this white dome. Many reflective meters have a white dome also, so they can take incident readings. Most professionals, though, use a separate incident light meter. It's an averaging meter and works much in the same way as a reflective meter reading from a gray card. The major difference is that it measures light hitting the subject. Light is diffused by the dome, as it is diffused when it strikes the subject. And since the dome is three-dimensional, it is able to average out the light hitting it from several directions. For a reading, point the dome towards the camera. No matter what kind of light source you're using, be sure that you always get your incident meter close to the subject. That way you can ensure an accurate meter reading. Light ratios can easily be measured by pointing the meter at the highlight producing light and then again to the shadow area. An average can then be computed to determine exposure. Keep in mind the inverse square law. That way, by moving your key and fill light sources, you can adjust your light ratios. Incident meters were originally developed for use in the motion picture industry, and they have become the preferred system used by most professional still photographers. So far, we've been talking about constant light. But how do you measure the extremely short bursts of light typical of flash or strobes? The flash meter is an incident meter that is capable of measuring light in very short bursts. For the photographer's convenience, the flash can be triggered from the meter itself through a sync cord connected to the meter. But what if you're just using an attached strobe? There are some systems that can automatically sense the amount of light reflecting back from the subject and shut off the strobe when the proper exposure has been reached. But there will be times when you don't want to use the automatic system and you might want to override it manually. Or you might be using a flash system that does not automatically operate. In these cases, the exposure can be easily calculated if you know the flash's guide number. The guide number is set by the manufacturer and represents the unit's relative brightness output. Just divide the guide number by the flash to subject distance. Let's say my flash's guide number is 50 and my subject is 10 feet away. Then the correct exposure would be 50 divided by 10, or f5. Well, I think we've covered the most common forms of measuring light. Of course, there are other, more specialized pieces of equipment, but the principles are a constant. No matter how exotic or specialized the meter, it still will be measuring either reflected or incident light. In fact, many photographers seldom ever use a meter, especially when shooting in predictable light. Here's a common trick for shooting on a bright sunny day. If your subject is in the sun, just convert your ASA to your shutter speed and set your aperture at f16.
Key concept. In photography, light is measured by foot candles. Key concept. There are only two types of light meters, reflective and incident. Key concept. All reflective light meters are calibrated to read 18% gray. Key concept. A spot meter has a narrow angle of view. Key concept. Incident meters measure the light hitting the subject.
The light ratio is the relationship or difference between the key light, which is the brightest source of light, and the fill light or shadow. In this case, we have a 4-to-1 light ratio. That is, we have 4 times the amount of light falling on this side of our model's face as we do on this side. And since each f-stop represents a doubling of the light reaching the film, that means we have a 2 f-stop difference between the brightest and darkest areas in which we want detail. You'll notice that there are other bright areas, such as the backlight striking her hair, and the darker areas, including inside her hair here. This is a grayscale. It represents a range from the darkest black to the brightest white, divided into 10 distinct tones or zones. Incidentally, you will notice that the middle gray tone is the same as the 18% gray of our test card. This scale is the basis for what is known as the zone system. It's a method of exposure control pioneered by Ansel Adams, with each zone representing a 1-stop difference. The zone system photographer uses this scale to help in pre-visualization of the scene. Then by selective metering, this is where a spot meter is very useful, the photographer can select exactly where upon the grayscale each area within the scene should fall. Individual control over each frame's exposure, processing, and printing ensures that the finished print will have a range of tones identical to the pre-visualization. Since each exposure is individually manipulated in the darkroom, the zone system is best suited for sheet film formats like 4x5. But a lot can be learned from the zone system's emphasis on pre-visualization. We should all attempt to view the subject as we would like it to appear in the finished photograph, because through selective metering, we can exert a great deal of creative control over the subject's rendering in the final transparency or print. So far, we've talked about light and how to measure it, as well as the range of brightness or tones that make up the subject being photographed. There is another critical element to be considered when discussing exposure control. That's the film itself.
Key concept. A grayscale can help you visualize tones and zones.
The film's exposure latitude is simply the range of brightness that the film is capable of recording while retaining detail. Latitude will vary most between different types of film. Generally, transparency or slide film will have a narrower latitude than a negative or print film. Differences between brands within any given type of film are actually quite minor. When I evaluate a negative, I look for detail over the entire range of brightness, from the highlight to the shadow. Color and black and white negative films have a latitude of about 7 stops. That means the film should retain detail over a brightness range of 7 stops or zones on the grayscale. At first glance, this negative appears good since it is not too transparent nor too opaque. But to make sure that it will print well, I need to look a little closer. The highlights, which are the darkest areas, since this is a negative, should have good detail. And likewise, the shadows and the dark areas, like this hair, should also retain detail. The relatively wide latitude of negative films makes them somewhat forgiving. Unfortunately, that's not the case with transparency films. If you're shooting slides, you'll find that their latitude is less than 5 stops. And since in most cases the slide itself is the final product, what you see is what you get. A miscalculation of a single stop can ruin the shot. Because of this, most professionals will bracket to ensure the best possible exposure. Bracketing simply means that a second and third exposure are made at about a stop on either side of the indicated exposure. To most amateurs, this may seem wasteful, but for the professional whose reputation rests upon coming back with a shot time after time, it's inexpensive insurance. But bracketing is not a substitute for good exposure techniques. Always work to achieve the best possible exposure and use bracketing for the important or difficult to meter shots. Here's another hint. When you're shooting with negative film and the lighting conditions are difficult, expose for the shadows. The film's relatively wide latitude will allow detail in the overexposed bright areas to be brought out in the darkroom during printing. If it is desirable to bracket, then you might want one exposure at the average meter reading and then one more metered for the shadows. A film's latitude can actually be altered to a certain extent in the darkroom. By overprocessing the negative, the latitude is decreased. This is called pushing the film and results in increased contrast. Conversely, underprocessing will increase the film's latitude. This is called pulling the film and decreases contrast. Although pushing and pulling are techniques that you can use to shape the characteristics of any given film, in most cases you'll be processing your film in accordance to the specifications or having an independent laboratory handle the development and printing. Because of this, it is very important that you know the specific characteristics of the film. I would suggest a series of test shots to see for yourself just how many stops of latitude you can expect from the film you are using.
Key concept. Negative films have a wide latitude of brightness range. Key concept. You can manipulate the film's latitude by pushing or pulling. Film versus digital, which is better? When will digital replace film? Many photographers argue about the answers to these two questions, and that's too bad. The real important question to be answered is how can we craft better images with the tools we have? Film-based photography is still the norm in the professional world and will continue to be so in the near future. But that doesn't mean that most professional photographers don't use digital capture, because they do. In fact, about 80% of professional photographers use digital cameras. Images captured on the digital media are not the same as images captured on the film media. Let the end use of your image help you decide which media is best suited for your use. If I'm shooting expansive landscapes, large interiors or exteriors, or crafting images where color volume and contrast are important, then I use the film media. If, on the other hand, the end use of my image is to be offset printed or digitally printed or posted to the web, then I use digital images. Why? Let's compare these three images, shot on color negative film, color slide film, and the digital media. All three of these images appear to be just fine for publishing or being sent out for printing or printed in-house. But all three images are also different. Here's how. The image from the negative has less contrast than the other two images and less color volume or saturation than the other two. The image from the transparency has more contrast and more color volume or saturation than the image from the negative film. The digital image has good color volume, somewhere in between that of the negative and that of the transparency, but also has the highest levels of contrast. This is because each media records light volume and light quality differently. If you look at any normal image you're about to photograph and study its range of brightness, that is, from its darkest shadow detail to the whitest highlight detail, you'll find a large brightness range. If you photograph your scene using color negative film, it can record up to 10 stops of this brightness range. If you use transparency film, you can record up to 7.5 stops of this brightness range. But if you use the digital media, you can only record 6 stops of this brightness range. Therefore, the digital format can offer less scene information and with more contrast. While my digital camera is a good addition to my camera bag, it won't totally take the place of my film cameras. But don't get me wrong, there are great applications for digital images. If the final image is going to be digitally printed for a magazine, catalog, book, newspaper, or new package design, it's a great format selection. Digital images are used for personal events in real estate, insurance, sports, and the news media each and every day. Digital images can also be used in the professional studio for such applications as portraiture and advertising if the photographer knows how to light for the digital format. Digital photography has come a long way over a few short years and will continue to grow in its popularity and applications in the coming years. It's a medium with a bright future if you understand its limitations. Key concept: let the end use of your image dictate the use of film or the digital media. Key concept: brightness range. The range of color or black and white tones from the darkest shadow detail to the highest highlight detail.
So far, we've been talking about exposures of anywhere between 1 second and 1/1000th of a second. But when making longer exposures, you will need to be aware of reciprocity failure. Normally, an increase in exposure will produce a proportionately brighter photograph. But when using long exposure times of several seconds or even minutes, this relationship may diminish slightly. Exposure meters do not take this into account since each film's degree of reciprocity failure will vary. Because of this, the film's data sheet should be consulted to help determine the correct exposure. Color films will also experience dramatic color shifts during long exposures, and you may have to filter them to produce the correct color values. Although this might be obvious, it's still worth saying. Anything that you put between the subject and the film, in this case a filter, you're going to have to adjust your exposure accordingly. If you're using a built-in meter, then the filter's effect is automatically being accounted for when the exposure is computed. If you're using a handheld meter, then you must compute the change in exposure based upon the filter's listed filter factor. An example of this is the K2 yellow filter, which has a factor of 2. This means that the exposure must be doubled or open up 1 stop. Likewise, this red filter has a factor of 4 or 2 stops. And if you're unsure of the filter's factor, you can always meter it through the filter itself. That way you will ensure correct filter compensation. Another factor affecting the film's exposure is bellows draw. With a view camera like this 4x5, the light falls off as the distance between the lens and the film is increased. Here again is another example of the inverse square law at work. One way to meter is to take your reading directly off the camera's ground glass, but chances are you won't have the proper meter at your disposal. If that's the case, the amount of exposure correction can be computed using a bellows factor formula. And bellows draw is not just a phenomena of a camera with a bellows. Macro lenses and extension tubes, commonly used with small and medium format cameras, will also require an increase in exposure as the lens is extended for close-up work. Fortunately, many of these cameras have built-in meters so that any drop-off in exposure can be compensated for automatically. A sunset is another time when it can be difficult to determine the best area within the scene to meter. I like to meter at the area next to the sun. If I meter directly into the sun, then it would become a dark tone resembling our gray card. But if I meter next to the sun in order to render the clouds as a medium tone, then the sun remains the bright focal point with rich colors surrounding it. Just be sure not to look directly at the sun through your camera. Another area that can be a real challenge for exposure determination is night photography. Obviously, if the subject is close, you can meter it directly.
Key concept: reciprocity, filters, and bellows draw can affect exposure control.
In the successful photo studio, there is really only one key ingredient: you, the photographer. That's because the artificial light studio is a completely controlled environment, one that is created by the photographer and is shaped only by the limits of his or her imagination. There are a few rules. It helps to have a large working space with a smooth floor and high ceilings. Of course, you'll want to block out any daylight or existing artificial light. Other than that, your studio starts as a blank, empty space. How you equip it is up to you. And that starts with the type of artificial lighting you choose to work with. Basically, there are three types: photo floods, studio strobes, and tungsten or quartz halogen. All three have their advantages. The photo flood is lightweight and inexpensive. They're a good way to get started. Studio strobes are fast. They put out a high level of light in short bursts. They consume little power and they stay cool to the touch. Many professionals prefer them. The advantage of tungsten is it's a continual light source. You can always see the working effects of your lights. But the important thing is it doesn't really matter what type of lights you're using. The principles of good studio lighting are always the same. So let's take a look at some of those principles. First, and most importantly, we always have a single light source, our key light. So no matter how many other sources you might want to add to your lighting plan, these secondary sources should always remain subordinate to your key light source. We'll look at some basic multiple lighting plans and how we would use them to light the human face in just a moment. But first, let's see how the position of the key light and its relationship to the subject will convey different moods, different kinds of information about the subject. If the key light is positioned directly above our model, the form of the skull beneath the skin is emphasized. The eyes are hidden in shadows. Visually informative, but not very flattering. Emotionally, the face seems lifeless. If the key light is positioned directly behind the camera, the inherent tonal relationship of the subject itself, eyes, hair, skin, and lips, are fully revealed. But the absence of cast shadows produces a minimal light and shade relationship, with a minimum of form and texture. This type of full frontal lighting is sometimes used for glamour photography, but unless your model has a perfect face and perfect skin, I can't recommend it. With the key light positioned directly behind the subject, only its glow surrounding the silhouette of the subject is emphasized. Backlighting like this reveals a minimum of form and texture, but strongly reveals the subject's shape. Positioned to one side, the key light produces a light and shade relationship with a maximum of form and texture. But this side lighting cuts the face in half, emphasizing every blemish and surface irregularity. Positioning the key light at 45 degrees, or halfway from the camera and the subject plane, is called quarter lighting or Rembrandt lighting. And it is by far the most popular technique because it's a good compromise. Quarter lighting produces a light and shade relationship that reveals form and texture and shape and subject tone. Let's use this quarter lighting for our key, and we'll add some basic secondary lights. But before we do, we'll adjust this just a little bit. If I ask my assistant to raise the key light slightly, her nose casts a triangular shadow on her cheek. And now if I move the key light towards the axis of the camera, the shadow moves directly under her nose. This effect is called the butterfly or paramount lighting. Okay, now what we have to do is fill in for those shadows. So we'll add our second light, the fill light. The fill light is usually placed as close to the camera's position as possible, so that way it doesn't create a second set of shadows. And one more thing, you want to make sure that your fill light source is only about a quarter or a half as powerful as your key light source. That way the two sources won't compete visually. And look what happens. That looks about right. Now let's add a third light, one that will accent her hair and separate her from the background. The hair light, sometimes known as a kicker, is usually positioned behind the subject, more or less opposite the key light. You'll want to have the hair light up high and out of the way, and you'll want to use the adjustable barn doors to keep the light from spilling directly into your lens. I like my hair light to be fairly directional and about the same intensity as my key light, or a little less. Let's see what this does. Okay, one last thing. We'll add a fourth light to bring out the tone of the background and add a little depth to the scene. The background light is usually positioned low and behind the subject. Its beam aimed away from the subject towards the background. Okay, turn it on. Good, that looks great. A typical lighting plan using 4 lights, but not necessarily the only lighting plan for this subject, and not necessarily the best one either, because that part is up to you. You're the one who decides how many lights you should use, because in the end, it depends on how you interpret your subject and what you want your photographs to convey. Thanks a lot, Jill. And that's really the thing about photographic lighting. It's more than just a collection of formulas and techniques. It's an interpretive art form with infinite possibilities. And that's how you should approach it. Whether you're using natural light, available light, portable flash, or multiple lighting placed just as we did, try all the possibilities and variations. Experiment, find out what works for you. And don't be afraid to break the rules. Remember, when it comes to lighting up the world, the sun does a pretty good job. What I mean by this is don't use 4 light sources when a single source will do the job. Keep it simple. Above all else, keep it natural.
Key concept. Studio lights can be photo floods, strobes, and/or tungsten lights. Key concept. A good studio lighting plan always has a single light source as the key. Key concept. The best lighting plan is always determined by the photographer. Every art form has its own specific medium. For that of the photographer, this essence is light. Without light, the photographer is as stymied as a potter without clay, a painter without color, and a writer without words. It is therefore all the more surprising that many photographers take light for granted. They pay attention only to its brightness. They neglect the fact that light manifests itself in many different ways. The visual spectrum has direction, form, contrast, and color. Light can be as soft as a single candle or as bright as our sun. It can be direct light, diffuse light, reflected light, and even filtered light. It has to be measured and manipulated if our photographs are to be successful. Sometimes light itself can be the subject of your image, while other times the use of light will only complement your subjects. Light is complex, fascinating, and always changing. No matter what kind of media you are shooting, film or digital, you must study and understand light with all of its nuances. Then, when you work with hard light, soft light, backlight, colorful light, your images will make a statement. Because in the end, any image succeeds or fails by this essence of light. I'm Brian Ratty. Thanks for watching, and good luck and good shooting.